Hey guys, this is Quentin. People call me Q in MGH radiology. Today we will cover the iterative image reconstruction, and I believe you have know some basis of reconstruction. In this course, we mostly focus on iterative image reconstruction. And if we have time, I will show several slides about, how can we do deep learning based image reconstruction and the same kind of framework. So I get the slides from George, from Richard Leahy, who is my PhD advisor, Jeffrey Fessler, who is a mentor to me for a long time. And Jeff has very nice slides and a draft book that is the best on this topic. So probably you have seen the reconstruction from FBP and OSEM. You can see that compared with FBP, OSEM give you much better result. FBP is a very traditional reconstruction method that is purely based on mathematics without considering any noise characters of your data. And OSM is very simple iterative reconstruction, but right now that's the mainstream for commercial PET scanner. You can appreciate that compared with FBP, OSM already get quite good image quality, but compared with the result in nowadays with some penalized maximum likelihood reconstruction like the Q-clear by GE, this image quality is much worse. So why we want to do iterative reconstruction based on statistical method? Because in this way, you can put more physics and apply information into your modeling in your reconstruction. For example, you can add object constraint like non-negativity and accurate physical model. Right now, for any imaging device, you need to do a lot of corrections, and you can put all these corrections in a statistical model. And of course, you can consider that the noise properties of your data, particularly when you don't have many counts. So you cannot simply approximate your noise as a Gaussian noise. Also, you can put site information, like if you do a PET reconstruction, you can put the MR or CT of the same subject into your reconstruction, because in nowadays, almost all the scanners are hybrid scanner, meaning that you have multiple different modality, and you can use the information in one modality to another modality. And you can consider a lot of non-standard geometry. The traditional FBP is purely based on mathematics, so there are quite some underlying assumptions. And when you validate this assumption, you get a very severe artifact. And iterative reconstruction is more flexible in this sense that even for irregular sample or missing data, it can still give you a quite good result. But the disadvantage that is computational time, model complexity, and software complexity. Over time, because the improvement in the computational industry, this becomes a very, very small problem. And in nowadays, almost all the computers has a GPU, and that can greatly facilitate the computation and make these more complicated algorithms practical in a clinical environment. So it doesn't mean that the traditional method doesn't work out. It does have some very nice property. For example, its idea is based on ideal mathematical model, and For example, FBP is actually linear. It's a linear operator, which means that some property you know in your data can be easily translated to your reconstructed image. For example, you can consider your reconstructed image's noise that is a linear mapping of your raw data's noise. So then you can easily characterize it and do more statistical analysis. This is the biggest advantage of this traditional method. It's still used in nowadays. Okay, here shows some example. This shows like the two images FVP. This is piecewise penalized weighted least square. That's a very simple iterative reconstruction based on Gaussian assumption of your noise. And this penalized likelihood is based on the Poisson likelihood, which models the noise better. You can appreciate the improvement of image quality. If you look at normalized mean square error, then penalized likelihood that gives you the best result in terms of computation. So the advantage of PET and SPECT, we always say that is molecular imaging is very sensitive and quantitative. So if you don't have a good reconstruction, you look at the normalized mean square error, you cannot take advantage of the quantitation characters of your PET imaging. So that's why iterative reconstruction is really needed. Here it shows some examples of the benefit of iterative reconstructions. First, you can put a physical model inside your reconstruction. Here give you a very nice example. If you use copper isotopes to label a tracer, then because this isotope, when the positron annihilate with electron, is travel some distance, and for different isotope, the travel is different. So this is the curve that's called the positron range, meaning what's the probability and what's the distance that the positron travel before it's annihilated. So if the travel a long distance then annihilate with the electron, then you get a very blurred information, because what you measured is the 2 gamma come out with this annihilation. So what you measured is the positron after its travel to some distance. So it's a blurring effect. You can see that they have different kernel. And if you look at the images, actually very blurred if you don't put this positron range modeling inside your reconstruction. If you look at the FDG, and if you use iterative reconstruction with, this is without positron range, and with positron range, then you can see how much you can recover the original resolution of this scanner, and you get better, a much better image and a much better quantitation. So another case, for example, this is another very interesting case. This is called zoom-in PET. What it do is that, so for a PET scanner, right now the resolution is about 4 millimeter. If you want to detect smaller lesion, one way you can do is that you put a PET insert that's like a small curve of PET detector with much smaller detector size. Then you put this close to whatever the site that you want to get a better resolution. Then you combine the data from the commercial scanner and the line of response between this smaller detector and the detector in the commercial scanner. You get a multi-dense sample during some small region of interest and get a much higher resolution in that place, and then you can detect smaller lesion. This is called PET insert. Traditionally, if you want to develop FBP reconstruction to do this, it's quite complicated. You need a lot of rebinning, resampling, and you can bring a lot of artifact into the reconstruction. With iterative reconstruction, you just model each line of response, and then it's much easier to incorporate this irregular structure into your reconstruction. The other case shows like OSM and FBP reconstruction for SPECT. And for whole body PET, these are a little bit old images. So this is an interesting slide. It shows the history of reconstruction for CTA and PET. So if you look at the history, there are several things which is quite important. The ART algorithm is introduced like in the 70s, even before the computer. So this Gordon is the Gordon Sentence Gordon. He's a great inventor. And the EM algorithm for Poisson data, that's one of the most cited paper in the field, and regularized or Bayesian Poisson emission reconstruction that's introduced in '85. The real software based on this type of algorithm actually come to commercial scanner just about 5 years ago. So you see, it takes so long for algorithm that work in academic setting goes to the commercial scanner. And OSM algorithm, that's very simple algorithm, but this is one of the most cited paper in our field. So this is the history. Let's go through this and look at, what exactly are these algorithms. So this is the important slide that if you can only remember one slide when you leave this lecture, this is slides you should remember. So this basically gives you a tree structure of all the popular or common used algorithm in the field. In the traditional method that doesn't consider any noise, you have FBP and BPF. So this one, you do the back projection first, then you do the filtering. This is a very nice, elegant method using the Hilbert transform. Very nice one. And for iterative reconstruction, if you think that you don't consider any noise of your data, then you can just use algebra to design your algorithm. Basically, you find the projection of linear equations. So this is mostly called ART algorithm. And if you concede the noise properties of your raw data, then you have two categories of algorithms. One is the weighted least square type of algorithm. In these algorithms, that you concede that your noise is Gaussian noise. So then it's very easy to design a likelihood. And if you solve the likelihood, then it's mostly like a least squared solution. But it's based on the assumption that you have enough count, enough data, so that you can approximate your noise model by a Gaussian model. And if you don't have that luxury, you don't have enough count, you still need to consider your noise model is Poisson model. Poisson model is much more difficult, so you need to design much more sophisticated algorithms to solve it. There are many of these algorithms. In nowadays, most of the research is focused on here, and most commercial reconstruction is OSEM and some kind of conjugated gradient method, the CG method. Okay. This is an important slide. So we just need to use one slide to introduce the ART algorithm. This is a traditional algorithm still used a lot in nowadays in other imaging modalities. What it do is one type of projection onto a convex set type of algorithm. Basically, you have your center ground Y and you have your image, you have a projection matrix P, you want to find a solution of X satisfy this equation. If you look at from the algebra point of view, that what you have is that you have initial guess, then you project your initial guess to the hyperplane defined by this equation. At the end, you goes to this column, at the head of this column, then you get optimal solution. This type of algorithm called the projection onto convex set algorithm. This is a very simple one. So I have a movie, but this movie doesn't show over here. So that goes to the second category, which is the one that based on a Gaussian likelihood. So if you assume that you have enough count, you can approximate your noise by Gaussian noise, then you can write your likelihood. If you calculate maximum likelihood of this Gaussian probability, then you can get some equation like this. This is like just L2 norm of your image. Over here is referred as FG is your data. It's like weighted L2 norm, weighted mean square, and you have a closed form solution. It's just that it's take some effort to calculate this weight. This is simple and it doesn't work very well because in nowadays, when we talk about the CT and PET, we always want to reduce the dose, which means that you will get much less the number of photons in your detection. So then you have to consider your noise as a Poisson noise. So then we focus on this type of algorithm in nowadays. If you have a Poisson likelihood, then you calculate maximum likelihood of your Poisson probability, you get a nonlinear function over here. So there's no closed form solution. You have to solve this in an iterative way. So the way that usually you do is that you have an estimate of your current image. You do a forward projection using your system model. Then you compare with your measurement. Then you calculate what's the difference. Then you use this difference, somehow adjust your initial estimate, get an update of this image. And then you do this again and again. At the end, this calibration, meaning your estimate centigram and your measured centigram has a small difference. So then you terminate your iteration. If you write in mathematics, basically this is like a step gradient-based updating. You have your current estimation of the image Fm, and you calculate the gradient of your likelihood. Then you weight it by something called a preconditioner, which is a function of your current image. And then you use a different step size function to adjust how much you want to update for each iteration. Then you correct your current image and get a new update, and you do this in a way that once this part gets to 0, meaning if your gradient reach to 0, then this thing equal to 0, then you don't have any update. That's the ideal case. You reach your optimal solution. So here shows like an example. This is a very simple toy problem. You have 3x3 images, and you have a measurement at different angle. Suppose that you have like 2 detector array over here and over here. This is what you measured. You want to estimate your image. So what you do is that you give like a uniform distributed image output 1. Then you calculate, what is the projection at each angle. Then you compare with this. Once you have this, then you look at what is going to be the measure, the projection that you should have in your detector, and you compare with that what you measured. Then you get an error. You back propagated error into each voxel, adjust that. Then you do this 1 step, 2 step. At the end, you get your correct images. That's basically all the iterative reconstruction do. And when nowadays, people are talking a lot about deep learning-based reconstruction. There is one type called in-row type of reconstruction, particularly useful for MR. It's exactly doing the similar way. So the most popular iterative reconstruction based on Poisson likelihood is called MLEM. So what it does is that you calculate the expectation of maximized likelihood. If you write this algorithm in a mathematical way, this is the updating equation. So what it does is that this PKL is basically the projection of your estimate image, and this is your estimate synogram. You calculate the ratio of these two, and you use the transpose of your system projection to transpose this difference into image space, and then normalize by the sensitivity of your system, and use that to adjust your current estimation. This is the MLEM algorithm. So in this type of algorithm, there are two key operators. We call it the forward projection and back projection. Basically, what forward projection do is that given an image, and what's calculated is that if you have a system matrix that basically shows the mapping from image from each voxel to your detector measurement, we call this is a forward projection, basically from image space to the detector space. You can very nicely model this as a matrix times to a vector. Okay, this is forward projection. There's another concept called back projection. So if we look at this updating equation, that's almost universal for all gradient-based method. So if you write this in this way, this is the equation we just described, and you can rewrite this in another way, which is as following. Basically, you calculate the difference of your measured synogram and you estimate the synogram minus by 1. Basically, you calculate the difference and you normalize by your measured synogram or estimate synogram and calculate the difference. And this difference is back project to the image space, normalized, and then add to your previous reconstruction. So you can see that there are two important operators, the forward projection over here that we just described, and this one that you get the error in the synogram space, in the measurement space, you back project this to the image space, we call this back projector. So for iterative reconstruction, more than 90% of our calculation is spent on forward projection and back projection. Once you have forward projection and back projection, particularly after you have the back projection, then it's in the image space, the number of variables in the image space is much less than synogram space. So the calculation becomes very fast, and beyond the forward back projection, the computation is just like less than 5% for all the scanners. So here shows that if you have the system matrix and you have your measurement, you calculate, you back project this into image space. Basically what you do is that you calculate the transpose of your system matrix and turn this to your vector in a measurement space. So this one in the rectangle is called back projection. So the problem of MLEM algorithm is that it's very slow. It's very slow to convergence to the optimal solution. is also computationally very demanding. It's need a lot of iteration. And so how can you make it faster? You can using something called stopping rules. Basically, just stop your iteration at some certain time point, or you put regularization. The stopping criteria is very difficult to do because you need to consider different scanner, different study, different tracer. It's almost impossible to find a general rules to design a nice stopping criteria. And regularization, that's something you can do. We can talk about later. Even with regularization, you still need to take quite some time to get a good convergence. So it's still time consuming. The other way is to use our OSEM. OSEM is a very popular algorithm in nowadays. It's actually invented a long time ago by a professor at MIT in ECS working on control theory. At that time, they call it sub-gradient method. There are a series of papers about how to design the algorithm, all type of algorithm, and also how to analyze their convergence properly and which condition they were convergent. But in the pet society, nobody knows this type of algorithm, and people kind of reinvent it in about 2000, and they call it auto subset EMA algorithm. So the idea over here is actually very simple. So if you calculate, if you look at this part, inside over here, this is the gradient of your lecture function. And when you calculate this back projection is a summation. This summation is very large. That's related to the number of detectors you have. In the case of PET and CT, it's number of line response you have. The number is huge. And you know the summation is like averaging, weighted averaging. It's a low pass filter. So then, if you look at how this happen, you can get a sense that when at the beginning in your iterations that you have your solution is far away from the optimal solution. At this time, if you just use like one section of your data or one section of that summation to calculate, to approximate the gradient, you get quite good results. It's not optimal, it's not correct, but it's not far away from the correct result. And because you just use a subset to calculate the gradient, the computation is sped up dramatically. And you can do this, and then at the end, you will not converge to your right result. And then what you converge is going to be a sphere around the optimal solution. So at the end, when you do this updating to many iterations, then basically your solution will wandering around in a high dimensional sphere around this optimal solution. You cannot reach the optimal solution. So the basic idea is very simple. You just use a subset of your data to calculate the gradient, and then basically do forward projection, then calculate the gradient and do the updating. And at the end, you still get a quite good result. So this is called auto subset EM algorithm. In nowadays, people in deep learning also use similar way. They call it mini batch. So mini batch basically doing the same thing. It's approximated gradient, not by the whole training data. You divide your training data into mini batch and you update each time based on what the gradient you approximate using your mini batch. And whether you can find a good way to divide the mini batch and do the normalization, it's very important for your training and how can you get good training result. So it looks like this idea has been reinvented again and again, but it's all based on the same very simple, intuitive explanation. So this is all the subset method. So basically, right over here, this is more mathematics explain how you do it. Basically, as I said, that you use a subset of your data, calculate for back projection, and you can approximate this gradient, and then use that as you approximate to gradient, and then do the updating. So there are several key when you choose these order subset. For example, you want choose a way that your subset is select in a way that is balance each subset. For example, here shows the true gradient of this Chef-Logan-Fenton. And if you just look at the even number of projection and odd number of projection, you calculate the gradient. Then the gradient give you some difference. And when you use like so if you do it this way, basically your subset is choose in an even way, right? You choose each other projection as inside one subset. If you choose in another way, which is much unbalanced, that you choose like first 90-degree projection as one subset and another 90-degree as another subset, and then your gradient, your subsets is unbalanced. So in this way, that the difference of your gradient is big. When you use this to do reconstruction, you actually get bias, and you will never reach that closed sphere around the optimal solution. So how to choose a good mini batch or a good subset is important for this kind of algorithm. So the OSEM algorithm has become very popular because it's very fast. It gives you quite a good result. It's actually a standard reconstruction method in commercial scanner. But there are problems of OSEM. For example, the convergence is not monatomic. So meaning that for each subset, you may have fluctuation in your loss function. This is one problem. The other problem is that it doesn't converge. We know that it's converged to a large sphere beside of the optimal solution. It's also unpredictable, right? It doesn't converge and loss function change all the time. So you don't know what's the resolution after an iteration, what's the variance after an iteration. And if you want to, characterize like the quantitations of a tumor region, you don't know what's the variance. So these are the problems with OSEM. So the solution people coming out is for this algorithm is called incremental method. So this also started by the same professor at MIT in 50s. So the way that they do is that we have talking about that it's all based on gradient-based method. You have gradient, you have a conditional number, and you have step size function. So the step size function basically tell you if you know your convergence direction, how much distance you update at each iteration. So there are mathematics approach shows from 50s that if your step size function follows these simple rules, then it's guaranteed that you will reach a closed form solution. So what does this mean? Previously, we say that if you use subset, your iteration at the end will somehow reach to a sphere, the surface of a sphere close to your optimal solution. So This is based on that you use a step size function 1, right? Most algorithm, nowadays, most deep learning algorithm also use step size function 1. If you use smaller step size function, what you see is that this sphere gets smaller and smaller, right? And if you further reduce this step function, then this sphere will eventually collapse to your optimal solution. That's how it works. And this step size function just need to follow these very simple rules. When it's reach infinity, then the step size equal to 0, and the energy is smaller infinity. And if you add all the step size function to infinity, and then this increase to infinity. So these are very simple requirements. There are many functions can satisfy these criteria. Then how to design this step size function is a very interesting and tricky problem. There are many papers talking about this. The same criteria can be also used for traditional ART and other methods, right? And we also use this type of algorithm to do reconstruction. I have a couple of papers on this too. I'm not sure whether this is my paper long time ago. This is the way to solve the problem for OSEM. In nowadays, some people start to consider this also in deep learning. You can see very nice paper published over here. So here shows that if you use incremental subset method to do reconstruction, this is the FBP reconstruction. This is penalized likelihood reconstruction. This is the way that you use all the subset. In this method, that you approximate your Poisson likelihood using a surrogate function, which is another very typical category of image reconstruction method. We are not going to touch on this surrogate method. It's very nice, has very good properties and very fast, but we don't have time to cover this. But this doesn't converge. And if you use an incremental gradient method, then it will converge to the true solution. You can, this is called trios. That's for attenuation image reconstruction. So you can appreciate that the image quality increase a lot. And also the quantitation is also much better. Do you guys have any questions so far? Okay, if there's no question, let's go to next topic. The next topic is that if we can use incremental gradient to solve EM algorithm, whether it's good enough. We still have one problem that we didn't solve, which is about long space. So we know that the problem of PET and CT compared with MR is that our system matrix is low rank, meaning you can consider it this way, that the whole imaging process is like a low pass filter. So once you have your measured center ground data, you don't have enough information to go back to your true image. If you look at your system matrix, that it has, the rank is smaller than your measurement, which means that there is a non-space. So usually you have G equal to HF. F is your image, H is your system matrix, G is your measurement, right? And there exists something we call the non-space. Basically is a matrix Z. Z times H gives you 0. So if you only know your G, when you try to recover it from G and H, you want to get F. But if you get F plus Z, it still satisfies this equation. So you don't know whether what you get is going to be F or F plus Z. A simple case, a simple example over here is that for this system matrix, for this data, and this is the image. If we use ART, if we start from this random guess, then at the end, here is what we get. We have F plus Z. This is not our two images. That's our two image plus our non-space. And if we start from a uniform image, then we will get F. We get the two images. So this is a problem in our system. There's no way to avoid. It always exists of there. So now how can we get rid of this Z, right? The way we do it is that we bring some prior image over here. Like we say that F should looks like something and should not look like F plus Z. So if you have heard about deep learning, you have heard about GAN, right? This is very much like the idea of GAN, that you generate an image F, then you have a way to distinguish whether this is a true image or not. The traditional way people do it is to bring prior information into your penalty function in your loss function. So the other way to look at this is from algebra. So suppose that your system matrix can be, decomposed into eigenvalue and eigenvector. So then, if you have this linear function that your imaging system and your centigram, then when you calculate F, you basically calculate transfers of H plus G, the transpose of H, if you decompose H in this way, which is 1 minus of eigenvalue of your matrix H and the same vector. Now, your real, so you will never get this, pure measurement, right? Your measurement is always like your image forward projected plus some noise. So if you have this noise, you try to do the inversion, then what you get is going to be the transpose of your image F and also the noise. So if you look at these terms, basically is normalized, is amplified your noise M. So here shows that this is the eigenvalue of your system matrix H. And what you do over here when you calculate pseudo inversion, it's invert your eigenvalue, and then you see at the high frequency component over here, your noise amplified. So that's why if you just use OSEM, then the high frequency component of your image will get amplified. You see a lot of high frequency noise in your reconstructed image if you run many iterations. So you need somehow control this part of amplified of the noise. So that's why you need to bring regularization into your reconstruction. The simplest way in traditional signal processing people do is that they put a small value constant into the eigenvalue of here, and then when you do the inversion, it will not go very high, it will saturate at some time point. So that's the most simple regularization at early time. And in nowadays, the regularization is much more complicated. So here shows that some result, if you use, I need to speed up a little bit. if you use traditional FBP and conventional weighted least square based on Gaussian and EM algorithm, post-field EM algorithm, and if you modify it and use regularization, bring some simple prior knowledge into your image, you might get much better image quality. So all these statistics or regularized maximum likelihood algorithm, it can be formulated in this framework that you have a model for your data, a model for your image, and a system model. And then you put together, you get a cost function, which including the data fitting chain, which is likelihood based on your data model and noise model, and some prior knowledge of your image. And you put this as some kind of regularization. You balance these two by a hyperparameter beta, and then this loss function usually have some properties that you can use to design different optimization algorithms. And this is the 5 most important component in iterative or statistical path image reconstruction or any image reconstruction. So the first part is the data model. Basically, you assume your data is Poisson, you write Poisson likelihood, and then this is your maximized likelihood function. And the system model, you can consider a lot of things, particularly for PET. And in nowadays, when people are thinking about photon counting in CT, you also have a lot of physics that you need to model in a chain of physical process in the imaging. So for example, for PET, you need to consider position range, the geometry, attenuation, blurring. Blurring is caused by the structure of your detector, and sensitivity. Sensitivity is related to a lot of factors. So at the end, basically, you estimate like if there's a gamma ray coming from this voxel, what is the likelihood it will be detected along this line of response. If you model this, then you can recover the image. Really, this physics is the most important part of the reconstruction and for the resolution recovery. So the image model is also very important that bring your prior information and avoid, the non-space. So usually people design it in this way, that you have some kind of potential function, and this is designed in a way that gives you some kind of prior knowledge of your image. The simplest way people usually use is like calculate, in a label, in a defined neighborhood, and calculate some property of the neighborhood. This property can be smoothness, that our human eye like smooth images, so we can force some smoothness between the neighboring voxels. So you can use also some kind of Hoover function that favorite sharp edge, and or logical causal, which you can consider like these two are different balance between L1 and the L2 norm, basically quadratic. That is L2 norm. You can bring this type of prior knowledge into your reconstruction, or even better that, for example, in this case, that you have MR of the same subject scanned at the same time from a PET MR scanner. Then you can consider that there are some structural similarity between these two modalities. You can design entropy between these two images and use that as your prior function over here to do reconstruction. In this way, this is one of very early work that I did. So this is a Parkinson scan use Folipride. If you only use commercial scanner, this is what you get. This tiny structure called PAG. It has two lobes at two sides of the brain. If you use traditional method, you cannot see this, but if you use this MR imaging to help you recover the resolution, you can clearly see this structure. And this structure is indeed related to the dopamine D2 process of the neurons, and is strongly related to Parkinson's disease. And then if you calculate all these factors good, you can recover the resolution. Over here, it basically shows that once you do this, you get a very good resolution from this resolution phantom. And you can also control that different properties of your reconstructed image. In this case, that there's a prostate close to the bladder, and because bladder has a lot of traces, so you can hardly see the prostate cancer in most of cases. In this is the FDG tracer. So, but if you regularize that this activity inside the bladder will not propagate to the neighboring voxel, then you can start to clearly see the prostate cancer, and even see the shape of the prostate in this case. Here shows that the result, the reconstruction of FBB, OCM, and the PCT, which is like regularized likelihood method. You can consider this regularized version of OCM. So I'll give you one example why this is valuable. In nowadays, if you have 2 generations of PET scanner, usually the state of art is about $2 million, okay? 1 generation ahead of it is like $0.5 million. If you use a good reconstruction like this one on this $0.5 million scanner, you can get the similar result to $2 million use this OSCM reconstruction. So basically, this advanced reconstruction algorithm can fill the gap for $1.5 million for scanner. So that's why it's very valuable. And here shows another case that if you do the correct system modeling, image modeling, and noise modeling, then you can recover quality. So in this is a rat. You can even see the individual fingers of the rat. Of course, because this is a PDF, you cannot see it that clear. But if you go back to the original publication, you can see it clearly. And also, when you, particularly important is that for PET and SPECT, we always emphasize is a quantitative imaging modality. But it's not that quantitative if you use OSCM. If you use better, you only use better reconstruction, that you can realize you can fully take advantage of the quantitative characters of this scanner to make it the measurement quantitative. So here shows that for this phantom, when you use a map reconstruction, that the computation is really good, is close to ground truth. And here's the important slide that I want to show, that different category of reconstruction, particularly for iterative reconstruction. If you don't consider the noise, you use algebra knowledge to solve it, is ART type of algorithm. If you consider your noise, Gaussian noise, then is at the end is equal to weighted least square method. And if you consider more complicated Poisson noise, then your method is going to be all kind of EM or contrary gradient type of algorithm. And here is the important slide. The second most important slide is that your statistical reconstruction has these 5 components. And when you put the 5 components together, then you have a complete algorithm. And all the innovation in this field is around some kind of innovation or improvement in one component of this framework, even for deep learning. So this one part of this course. Do you guys have any questions? Okay. So if you don't have questions, then let me show you something else. Let's go back to here. Okay, I will use the rest of time talking a little bit on about deep learning-based image reconstruction. Okay. Deep learning-based image reconstruction. Okay, let's start from next slides. You know, we all know that deep learning becomes so popular in our day. If you go to all this scientific conference, like almost for all the medical imaging conference, like 80–90% of the talks are about deep learning. It's very popular. It just has been used in detection, classification, segmentation, and reconstruction, of course. The reason that deep learning becomes so popular, that's because it's a very good model to represent your image. So in the past, we have used all kinds of methods to represent an image, like the simplest way to use Fourier transform. Then later on, after the 90s, people start to use total variation, use wavelet to represent an image. And in the first 10 years after 2000, people start to use diction learning, basically use all kinds of kernel and diction to represent an image, and learn that kernel or the diction from data, using data-driven method. After people start to use deep neural network, it soon turned out that it's even better way to represent images. So the power to express image from deep learning is really, really big. That's why we can use it to in all kinds of medical imaging analysis and reconstruction. So there are already a huge amount of work to apply deep learning into image reconstruction. It has supervised method and supervised method, or semi-supervised method on all kinds of structures, ResNet, UNet, and used in MR, CT, PET, ultrasound. Ultrasound becomes very popular nowadays. There are several groups are focusing on this work, and the results are quite interesting. So you have seen these slides, like this is the third time. Basically, this is the framework of iterative reconstruction. And when you consider like hundreds of publication on deep learning based image reconstruction, you can always put that into this framework. So what people usually do is very simple. Like more than half of people working on, let me get a pointer. So like more than half of people working on this, like use deep learning to get as a prior and they use this as an image model and regularization to your reconstruction. Basically, they consider, you have a huge amount of data, and you learn, like for this data, what should be the property and the representation of the image you are going to reconstruct, right? Then you use this as a penalty function in your reconstruction, then you do a deep learning based reconstruction. The other way That very much like dictionary learning or kernel-based method. That over here, that you have you think that your image is a projection of your measurement is a projection of your image, and instead write your image as a linear compilation of Wavelet transform, for example, or Fourier transform, or kernel or dictionary. That's all linear method, like linear combination of the basis function, all type of basis function, all type of linear representation. In deep learning, you can write your image as a nonlinear representation, which is your whole neural network. So you replace X by a neural network, and then when you do the reconstruction, instead of estimate X, you estimate the parameters for your neural network. You can, when you do the reconstruction, you do training at the same time. So basically, you have a new data model you embed into this framework and do the reconstruction. If you consider another type of reconstruction, which is called enroll type of reconstruction, what they do is that you enroll your iterative reconstruction over here, your updating function, then you put each operator as a block in a neural network. So that's called enroll type of reconstruction. That is most popular in MR, but when you apply to PET and CT, particularly CT, usually you have a problem of memory, because in PET and CT, we consider 3D reconstruction, and particularly for high resolution CT, it requires a lot of memory. And one drawback of current GPU design is that each graph computational unit has like limited number of memory. It's not designed for memory-hungry application like CT reconstruction. So there's a limitation over there. That's why enroll type of deep learning-based method doesn't work very well for CT and MR, CT and PET. So that's the other block we're talking about, right? And for system modeling, you will think that is physics. There's not much work done over there, but the truth is that people are really creative. There are a lot of work also done in the system modeling. For example, people has used, deep learning to calculate the scatter correction for PET and SPECT. So right now, when people calculate scatter correction, they use single scatter correction. Basically, you do the simulation to calculate scatter just once. If you do multiple scatter correction, then you get a much better result. But you cannot afford to do that for reconstruction because the computation. And you use deep learning, you can get a very good balance about the computation and accuracy. You can use a single scatter correction to predict what should be multi-scatter correction using deep learning. And there are a huge amount of work to calculate attenuation correction for PET MR. My lab has like 5 journal paper on that already. So that's another very hot region. So basically, if I'm going to write a review paper on deep learning and image reconstruction, it can totally fall in this same old framework. So then you can see that the innovation in this field is actually bring a nonlinear representation of your image into your current framework and improve the result. That's what's repeatedly happened in the last 45 years in medical imaging, and it will continue to happen again and again. It's kind of, you can predictable. So basically this is like a very high level of summary of all this deep learning based image reconstruction method. Do you guys have any question? So, did anybody have any experience to do a deep learning based, image analysis or reconstruction? Thomas?
Yep. I mean, I've been working a little bit. Sorry, I was on mute. I've been working a little bit with deep learning in completely different fields of physics data. So we worked a little bit on trying to predict evolution of galaxies. So completely other end of the physics spectrum. But a lot of methods are very similar. I'm actually curious on one side of your remark here, which is kind of the memory requirements. Do you think that this is something we'll actually, like, coming from dual CS physics background, it's always interesting to see how exponentials chase each other. So do you expect that the exponential of making the problem more difficult by having better scanners outweighs the exponential of having faster computers or not? And that kind of could give me some insight of where the field will go in the next 3-5 years. Could the GPUs catch up, or the actual target moves faster than the chaser?
Yeah, so definitely the GPU will move faster, and we have seen that in the past. But the key point is not which one is faster. The key point is that for deep learning, once you do the training, right, the inference is very fast, right? So what takes time is the training. You may take a lot of time to do training, but when you start to apply it, do the inference, it's really fast. It's even faster than regular reconstruction. That's one advantage of deep learning based method. Let's give you an example, right? You guys, I don't know whether you guys heard about this new NLP tools, GPT-3. Probably you didn't. So that's a huge neural network. Basically, it take $460 million to train that neural network, meaning that people's human time, data, and computational power. So not many companies can do that. But once it's trained, when you try to use that neural network to use it in some application, it's very fast. It's extremely fast. One very interesting application, for example, is that you can use that NLP tools to actually make fake news. It's really, really real. Like if you design two characters, like if you design like one journalist in, let's say, CNN, interview President Trump, it can totally mimic their tone and their style of speaking and make fake news. So it's very much like their own style. And when you do this, you don't need to actually retrain everything, and it can do it by itself. For the example of sketch correction, that's first done by the GE Global Research Center. What they do is that it's taken quite some time to collect the data and curate data. Basically, for the data, they calculate both single sketch correction and multiple sketch correction, and they just train a neural network to map the single to multiple sketch correction. Once the network is trained, and when they apply to reconstruction, they just calculate single sketch correction, and it goes through this not middle size neural network, and then get something close to multi-sketch regression. So that's a perfect example that the training takes some time, the inference take much less time. So the point is like the inference really take much less time. The other example that from my group is that I don't know whether you guys heard about kinetic modeling, right? So you can estimate the kinetic parameter for each voxel, and we call it parametric image. You can do that after you do a reconstruction for each frame. We call it indirect method, or you can do it using SandGround directly calculate the kinetic parameters at each voxel. We call it a direct method. Direct method gives you much better result, but it's almost impossible for any lab to use it regularly because the computation is just too high. And for clinical side, there's no way they can use it. So then we basically curate and collect a bunch of data. We do it both indirect estimation and direct estimation. And then we use a neural network to map indirect estimation to direct estimation. But this takes a lot of time. But once this is done, in a rare case, when we have the indirect estimation, we can quickly get a result similar to direct estimation. So the inference time is very small. So I think that that's a more important point than whether exponential computation is important or exponential growth of computation power is winning.
All right, right. Thank you so much, Professor. So that actually clarifies kind of the follow-up question I had, whether the memory requirements are something that strongly impact inference or strongly impact learning. And apparently, just learning is actually the inference is actually doable on today's hardware.
Yeah. So the other thing is that if you talk to MR reconstruction guy, they are always, particularly for people doing this in-row type of reconstruction, once you train the neural network do reconstruction actually much faster than traditional iterative reconstruction, because it's just needed to do inference, and a lot of things has been learned from the data. So any other question? I see somebody from MIT Lincoln Lab, Jay. Have you done anything using deep learning?
Yeah, so our team is using it for ultrasound image analysis.
Like using some time for deep learning to beamformer?
No, not for hardware development, purely for the image processing. So just identifying key features and making diagnostic decisions based on images.
I see. We have one project on that too, to detect numerous wrecks from ultrasound imaging in the ED department.
Okay, gotcha.
Yeah, so a lot of knowledge that you use over here can be also applied to medical image analysis. The problem of medical image analysis, particularly for ultrasound, the question is that particularly if you want to get something that can be really used in the clinical environment, the data is too complicated.
Sure.
The data quality is really varies a lot depending on the operator of the ultrasound. So then your method need to be really robust.
Right, that makes sense.
Yeah. Anybody else has any question? Okay, if not, I think I have some examples of use deep learning to do reconstruction, but it will take another lecture to explain all of this. Today, I just want to give you guys really the big picture and the landscape of this topic. In the future, if you guys in your research, if you have any question related to, iterative image reconstruction or inverse problem, which including denoising, image restoration, image painting, and so on, feel free to contact me. I have a lot of tools and code that you can use, or you have some problem that you don't know why it's happening. I have great experience on all kind of inverse problems. So come to talk to me. I may be able to help you. All right, so we can finish today's course like 5 minutes earlier.